start the recording. Is my screen visible with
Yes.
the WWCode?
Yeah.
Sure. So again, welcome all once again to an interesting session on Women Who Code. So let me tell you a brief about what Women Who Code and what are the mission and vision of Women Who Code are, and about the speaker for today and the session. So Women Who Code is a global non-profit organization which is dedicated to inspiring women and helping them uplift in their technology careers. And we envision a world where all the women are proportionally represented as technical leaders, executives, founders, VCs, board members, and software engineers. So, the code of conduct of Women Who Code is that there is no discrimination based on gender or identity, expression, or sexual orientation, ability, physical appearance, or anything else that is listed here. So, that is our code of conduct. And so there are many ways where one can become a part of Women Who Code or get associated with Women Who Code as a presenter or a facilitator who is helping in getting the meetups arranged and get speakers or get the latest trends that people would be interested in, and as an audience. So those are the ways in which you can get associated with Women Who Code. And do check out the meetup links and the social links that are available for people who can follow us on Twitter, on Instagram, or the Global Women Who Code links also. So these are some of the links. And there is an interesting opportunity that is available for women who has taken a break and are aspiring to come back to work. This is a different program that offers VMware certifications on three levels of certification, which can be taken at a self-paced way by women who are currently on break and can give certifications and like acquire certifications and become a like talented workforce that can like boost their resume and come back to the work like come back to workforce. So do refer to any of our colleagues or anybody who is interested and currently on break to visit this Tara website. And without further delay, I would
Ranjani, there
like
is a
introduce.
question in the chat window which is asking if one is interested to become facilitator, okay, what to do?
Yeah, you can write to like you can visit the Women Who Code global website, and you can feel free to write to the email ID. So one of us will respond to you with the session details that you are willing to, like wishing to conduct, or the topic that you are willing to present. Those details will be like we would be responding back to you. Please feel free to write to that email address in the Global Women Who Code uh, website. And yeah, sorry, I missed introducing Mini. So the session for today is introduction to fractals, and it is something different from whatever we have had, like the technical topics around latest technologies and some things related to Kubernetes or the artificial intelligence, machine learning, or cloud related technologies. So this is something different. So I am also interested to know like what I can learn from this session. So this is an introduction to fractals, and the speaker is Mini, who is a principal engineer in measurements and analytics at ABB Ability Innovation Center, Bangalore. She holds an MTech in embedded systems from BITS Pilani and degree in computer science and engineering from University of Kerala. She has experience in defense, semiconductors, consumer electronics, substation automation, and industrial measurements. So we got her like acquaintance during the annual Connect conference, and we are happy to have you, Minnie. So let us see
Thank
like
you.
what else we can learn and what all we can explore from your talk. Thank you for accepting our invitation and presenting here. So I'll
Thank
stop
you. Thank
sharing
you,
and over
Ranjini.
to you, Minnie. Thank you.
Thank you. Thank you so much. Thank you for the nice introduction. I will begin to share my screen once again. Now, is my screen visible already?
Yes.
I'll switch on my video for a moment. I think probably I'll switch it off after a while. Okay. So that's me, because have some familiarity. After that, I'll switch off and then we'll continue and focus on the contents. And I'm very happy to see that there are some familiar faces who is inside, especially Shubha, Nisha, and all that. Very happy to be talking to you people in some kind of a presentation time after long time. And you can type in anything that you want in the chat window. I'm seeing the chat window also. May not be continuously, but at least off and on, I will have a look. And if I go too fast, please stop me. And you are also free to stop anytime and ask any questions. The contents are interesting. It's something slightly different. So the topic is about fractals. Introduction to fractals, and thanks for Women Who Code for arranging this session, because this is a topic which I'm very fascinated about, and I'm doing it for quite some time in my hobby time. So this is not my work, it's the time pass interest. But even though it is time pass interest, I'm doing it quite seriously because somehow I like the topic. So let us start. Okay, so let us understand the term fractal. This is about giving respect to the person who coined this term called fractals. Ranjini, I'm stopping to see that chat window. If there are questions, you please let me know. I'm closing my
Yeah,
chat
sure,
window
Minnie.
on. Yeah, thank you.
Yeah, yeah, sure.
So let us see who came up with all this, and the person who introduced this concept of fractals, so that we is this window also, maybe I should minimize it. Okay. So that whoever gave me so much of pleasure and enjoyment, so it is good to know who that created all this. So if you look at computing long ago, long back ago, computers did not have so huge of a computing power. So if you are looking at old microcontrollers, they only could do only very less amount of computing. So this complexity and these patterns that are hidden behind these numbers, they were not that easily seen, for the reason that you could not afford to have that level of computing. Just give me 1 minute. Let me just put some timer on so I'll have some control on time. Okay, thank you. So this is a person who is known as Mandelbrot. So this Mandelbrot was an IBM engineer, so who used to work on these computers in the early days of heavy computing time. And at that time, having the computing power available at his disposal, that was the time that these fractals came into being, or the discovery of this computing and the equations of nature came into visibility, though it was always like that. So that was what we are seeing. This is a very fantastic world to understand, because this is a universe in itself. And this Mandelbrot is the person who coined the term called fractal. And he's also known as the father of fractal geometry. So if you look at nature, like when you see a lot of walk around, and if you see around nature, you will see a lot of fractals. The moment you are recognizing the patterns, you will see a lot of them. So if you are more interested in knowing about the person, Yale University has a dedicated page where all his works are put on display. So all his writings, papers, publication, everything is there in Yale University page. And there is a TED talk. The video is available. It is called The Fractals and the Art of Roughness. And if you are thinking that when did this all happen, it's not too long back. See, like he passed away only in this year 2010. That is very recent. It is only 2020 that we are talking. So this is the person who came up with all this concept of fractals and who coined the term called fractals. And that is what we are enjoying today. And this is about infinity. Like we will come to that later. It is all about infinity. And what we see in nature and what we see in the universe around, that is all to do with infinity. I would suggest that you have a look at that TED talk, because that is very interesting TED talk. And then about me, as Ranjini introduced me, I have done my computer science engineering, and primarily I'm a programmer, computer engineer. That's what I am. And I learned numbers for a hobby interest. That fascination for numbers was always there. Like if you see the audience here, like some of them, they know me from my college days itself. There was some hidden number interest which used to be there. That is what popped up and then got me into this fractals. So I'm learning this more like a hobby interest. And the fascination for complex numbers, that's what got me into this fractals. And once I am into it, like I off and on, as I keep getting time, I keep doing it. So this is a way of seeing the world through these numbers. So now my challenge is that as I find so many things around, instead of just finding the beauty of things, you are seeing the numbers. So I do not know whether the number is more beautiful or the picture is more beautiful. That is what the challenge that I'm facing right now by seeing this kind of understanding in mind. So you see a tree there, then you do not know whether you have to see a tree and green and picture, or whether you are supposed to see numbers and equations. So that mix is something, sometimes it creates one confusion, but still that's also something which I am enjoying also. And let's see what are fractals. So fractals, this is to do with self-similar structures. So self-similar means at different scales, they all look the same. So you get into the different level of scale. The more and more you get into details, you will again see the same thing happening again. So that is what all about self-similarity. The complex patterns, so they are very complex, but then uh, it's not like a long partial differential equation with so many things inside. That's not the way we are talking. It has its complexity. At the same time, they are very similar and very same, and then that same pattern repeating. And if you zoom into a fractal, and then it's like you are walking into the infinity. As you get into the deeper and deeper into it, you will keep seeing the same pattern again and again and again. That's what you will see in a fractal pattern. And it is repeating a simple process over and over. It's not like there is a very difficult, it's not about difficulty, but it's complexity. And there is a difference between complicated and complexity. So what we are talking is complexity. Complexity is a behavior pattern that you will see about the systems in the nature. So you can see right now on the right side, like geometric fractals, these are the ones which, if you look at a triangle on top, these are known as Serenpsky fractals. If you look at the triangle and divide it, you keep dividing it, you will keep getting the same patterns. You divide it into multiple parts, and you again repeated the same pattern on one triangle and every other triangle, and you keep going inside. So your dimensions of the triangle may come down and down and down and down, but it never reaches zero. So it doesn't disappear. It will keep going on and on. As you walk inside more and more, you will keep seeing the same thing again and again. That's what I'm trying to show here by these geometric patterns. So these are known as geometric fractals, because we are creating out of this 2D geometry or 3D geometry. So down you can see one which is a 3D geometry based one. See, that is a cubic fractal. You take the cubic and then you creating the same pattern again and again, then you will get here. So there are so many in my system. I'll show you at the end of the session if there is time. Whatever I have done over this period of time, there are so many. I'll show you some of them. Then to continue, let us look at some of the fractals that we see in nature. So these are the patterns which I just copied from internet, these pictures. So they are repeating patterns. If you look at the first one, the ferns, what you see is that stem of the fern is there, and then the side petals you are seeing. But if you look at that one petal again, it has the same pattern once again inside. So if you are given the entire fern, or if you are given only that one part of that fern, just by looking at it, you do not know whether it is a whole, whether it is only a part. You are somewhere, but you do not know whether you are in the beginning, or whether you are inside, or whether you are in the infinitely inside. That you cannot make out. That's what the beauty of fractals altogether. These are all some of the other patterns that you will see in nature. Like trees, tree structures are very easy to see. The branching out, it will keep branching out, and then you keep going. You see, like if the structurally, we are talking structurally, given a tree branch or given the entire tree, you do not know like whether it is an entire tree or whether it is a branch. I'm not talking about the roots here, but the structure of the tree in itself. It's the same with these veins, lungs, and the seashell patterns, the human retina, blood vessels, even flowers. These are all nature fractals that you see in the nature. So let us see something which pictures which I have created myself. These are the ones which I have created, especially these are very explicitly showing this self similarity. That is why I put these two for an example. And then here what you see is the right side. If you see, you have those 2 patterns, 3 patterns, or 4 patterns. It's repeating 5, 7 like that. But if you look at the one piece of it, the one piece of it also is the same. In the similar on the left side, it is very similar to that ferns that you were seeing, the grass, the plant. So this also is very similar, but then I have made it a little bit into a feel of cubic structure. The entire stem given or the one piece given, you do not know. It's the same thing that is repeating. So it is infinitely repeating patterns. That is the self similarity that we are talking about. I hope the audience is with me. Is
Yes,
there any
Mini, very
questions?
much with you.
Then let us continue.
Yes,
So
Mini,
I think
continue,
I will.
please.
Hello.
Yes, Mini, continue, please. Very interesting.
Continue. Okay, so let us see one program. See, occasionally, I don't write all the program. Occasionally, I write some programs, but then sometimes I use ready to use program. So this is one Python program which is there for creating that triangle patterns which I was talking. So this is done with this turtle graphics and basic 2D geometry. Okay, you are just dividing that and then showing it. So we'll run this program. Oh my God, I have to show this side. See, you are dividing and going. This is a program which you were seeing that Serendipity triangle patterns. Like as you see, the beauty of it is this program at some point it is stopping. But if you don't stop and if you have enough of place to go inside, it's just that the dimension is coming down, but then it is keeping on going. Structurally, it is still the same and it keeps going. So these are the things which I do for a hobby interest. Like I just keep doing these kind of small programs where you can see this Mandelbrot set or the Serendipity triangle, or even some of those Lorentz equations and all that. These are one thing which like just for a demo I'm showing you. So if there are since this is a women who code session, so there, like if somebody is interested in coding, there is a lot of things that you could look at to see what is there around also. So I'll stop this one.
So there is a question in the chat.
Yeah.
Is there a GitHub with code for these fractals?
There might be, because some of the programs which I am using, like I don't spend money on this. So there are many programs which are ultra fractal and all that, which are should be there. I'll tell the name of some tools as we go along. So all what I am using is open source program because I am not spending money on all this. Uh, but there are paid programs also.
One other question is on books that you would suggest to read or learn to create these.
Books to understand the concept of the chaos theory in itself. I have read a book called Chaos, 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 as a book which I have read. In fact, that is the only one book which I have read. Other than that, I have studied from other public domain internet sources, like some of these data sheet and manuals of these programs themselves. Or I have also referred to many things from these maths packages, like this CoCalc or Mathematica or those kind of maths packages. I have learned many things from maths packages. And some things I have also learned from uh, graphics tools, like if you know these GIMP, Inkscape, and all those graphics tools are there, right? Graphics generating tools. From that also, some of them have these plugins for creating such things. So those are the sources which I have used. And what I saw was generally these textbooks in India, it was very costly. So that's also one reason I did not spend money on all this and to do that. But the internet, you will see a lot of material in the internet itself. So there are forums. I'll give you some links. In fact, I am also part of one fractal geometry group in the LinkedIn. If somebody is interested, maybe I can share that LinkedIn group. I am not maintaining that group, but that group is there, which I'm part of. Maybe, I don't see too many groups, but there is a group which, if someone is interested, you can join in.
Sure, that would help me.
Yeah, then
Please.
Let's continue. There's a group. I can share it at the end of the session. So now let us learn what is this concept of complexity. This is what we want to understand from all this. Complexity is, it's a, what to say, it is a systems feature that the system is complex when we say it means that the system is chaotic. So in the chaotic system, what happens is the very fundamental premise is a small change in the beginning of a system, a complex system, can lead to very dramatic differences in the outcome. That is what we are talking about here as complex system. Like, please do not equate complex as complicated. That's not what it means. Complex is a feature of a system, like the nature of being chaotic. And this is a nursery rhyme. So let us read this nursery rhyme. Then I think you will get that. For the rhyme says, for the want of a nail, the shoe was lost. And for the want of a shoe, the horse was lost. And for the want of a horse, the rider was lost, being overtaken and slain by the enemy, all for the want of care about a horseshoe nail. So what it is telling is about losing the whole war because you were missing a horseshoe nail. So this complexity is in that kind of a nature. Like small changes in the beginning of a system can lead to very dramatic differences in the outcome. Immediately, if we are so used to writing that y equal to f of x, it is not in that one iteration of y equal to f of x that the whole change happens from small change having huge effect on the outcome. But when we do it over and over, and when the system maintained for a long period of time, when that space and time becomes large, a small change can cause huge change in the outcome. That is what we call as a chaotic system. So if you are talking about mathematics, then it is beautiful and it is endlessly fascinating to call that a system is chaotic. That's what the term to use. If you can look at some kind of examples in Wikipedia and all that, you will see chaotic system. A lot of examples you will see. Some of them are about, say, how the market goes. You may not be able to predict from today to tomorrow, but over a period of time, you may not know what to predict because the system is chaotic. Small change can have large effect on the outcome. On the right side, you can see this is also called the butterfly effect. The butterfly effect is, it's a mathematical concept. At the same time, it has a philosophical angle to it. The butterfly effect is telling that a butterfly flapping its wings in Mexico that could be causing a hurricane in China. So the way it is telling is that small effect of the butterfly flapping the wing in one place, which is you don't seem to relate it to somewhere in the universe, but that causes a large change. A hurricane is a huge change. Like there is no proof to say that this is what is happening, but the principle behind chaos is this butterfly effect, small change causing large effect on the outcome. And it's not that the butterfly flapping the wing caused the hurricane. It's not that that is the sole cause of it happening. Instead, it is like if the butterfly had not there are so many other factors, but that one small factor also added to so that the effect occurred. If that small factor was missing, then it wouldn't have happened. So what you see there is it's a Lorentz attractor. So these are called attractors. The attractor is a term that we use for telling over a long period of time the system tends to converge into one place. That's what we call as attractors. Attractor, uh, like if you see some example, I'm not popping it up now in the interest of time. I think we may run out of time if I get into all that. But if somebody is interested, you can look at how a dual amp pendulum works. A dual amp pendulum is a very simplest example for a chaotic system. Otherwise, stock market, even the whole universe itself. Sometimes you could ask the question, like if the whole universe was one system, then we should be able to put the whole universe into equations, and then we should be able to predict what will happen to the whole universe over a period of time. Like if you look at from a maths point of view, you could say that, okay, like you could model your whole universe, but we are not even able to see do a small weather prediction itself what will happen over a period of time. Even the weather predictions themselves are approximations, and it will be correct for short interval of time, like tomorrow, 1 week. But then if you want to do weather predictions over a long period of time, like including things like bigger things like whether an earthquake or tsunami happens, ideally you should be able to predict, because it is all what the acting elements are what is already there inside the universe today. There's nothing new that is acting. All are existing. There's nothing new. They are only interacting with each other. That is how everything else is happening. Even the human mind also, it is only the existing things or what else you are putting inside, it's interacting and something else is coming out. So there's nothing unknown in that sense of unknown, but you are not able to model them. The reason is because of this chaos effect. If you have some small changes in the input, if you have not modeled that small item, then over a long period of time, it can have huge effect. So it is something else that would happen. So this mistake is something which makes long time weather prediction almost impossible to say what would happen. And Lawrence is one person who had worked, it is a mathematician who has worked a lot of time into it. So you will see these Lawrence attractors. There are a lot of attractors which are, you will see it in this chaos world. And when the attractor itself is a fractal, means it is having a self-similar pattern. When that attractor itself is a fractal, that is when you call them as a strange attractor. I think I'm introducing too many new terms, but then just understand that these are the way of looking at it. And then I told about how about looking at the whole universe as a system and then model it, and then we come out with it. It's a very weird, wild idea to talk about. Not practical, not possible to do.
Mini, can I
But
invite
then,
you, please?
yes.
Mini, can you just explain what is an attractor?
Attractor is a system, a chaotic system. A chaotic system over a period of time, it will converge into one place. That is where you call as an attractor. Where it converges to, that is where we call it as an attractor. A chaotic system will remain chaotic. But at some point it will get into, you can identify patterns of emergence that would happen in a chaotic system over a period of time. So emergence, you could look up even the term called emergence in Wikipedia or somewhere. So this is a phenomenon that we call as emergence, like something which you have never anticipated, like properties new which you never thought of come out. Some people like these team building people or the soft skills trainers also might use terms like team synergy. Like you may say that, okay, it is like 1+1 may be more than 2. It's not the more than 2. Like over a period of time, if you apply this emergence philosophy, new things which you have never anticipated will come out. Did I tell you?
Okay, okay, Mini. Sure.
These are properties of generally what we from chaotic systems. So then to come out with this was something which I learned recently. If you say that the whole universe you cannot do the modeling, if you look at as computer science engineers, we have a tendency to look at, or as programmers, we have a tendency to look at, okay, we put it into a variable. If it is not possible to put into an integer variable, why not we put it into a real variable, no, a floating point variable that can hold even fractional values. But then that is only limited precision that we can do. We cannot go and put 10.0000 at 1 or 2 or whatever. You can't go infinitely there. So if you are really interested into understanding these real numbers, there is a principle which is they are available. They are still in these university professors might talk about it, that we call it as a BSS model of computation. That is the name of 3 scientists, some Blum, somebody or the other. So this BSS model of computation is how can you do infinite precision real numbers? Because real numbers, unless you are able to do an infinite precision, your model has lost that small values. So if you have lost the small values over a long time, you will lose it. So this is what we are talking about from the concept of complexity, chaos, butterfly effect. These are all the concept around these fractals. But ultimately, it is the same concept you are talking. If you are talking of complexity, small changes in the beginning of a complex system can lead to dramatic difference in the outcome. Sometimes this is some pictures which I have created. So systems and emergence. So new patterns will emerge. Sometimes sometimes I also have a personal way to look at it in a little bit philosophical manner. Like when we are doing some action, we think that, okay, well, let me help that person. I don't know whether that is working or not. We do not know what has happened actually. Ultimately, over a long time, what has happened. Maybe you would have explained something to someone. Even today, I'm doing this session. I have no idea what would happen over a long period of time. At the end of the session, so you may say it was nice or not so nice, or interesting or not so interesting. But then what leads to anybody to go further and to do something, like, we do not know. So whatever you are supposed to, you just do it, like, and then you continue. The effect will happen over a long period of time. Sometimes it takes away the discouragement of not seeing results immediately. So that is all about and now let us look back to mythology. I also have a habit of reading about these mythologies and fairy tales and all such kind of things. So if you see mythology, the only thing which I have come across in the mythological manner about fractals is, this is the only one item which I have come across. This is about that magic Indrajal that we're talking about. The term Indrajal is coming from a place from that Indra, that Indra is there, right? Lord Indra. That Indra seemed to have a net. So this is the best description which I could get from in an English version for the Indrajal. So the way, this is the description of the how that Indrajal net is. It's like it's telling that that net is made of pearls, and those pearls reflect each other. So what you will see is I don't know, this is a very long sentence, but still some of the lines I have highlighted and kept. So they are saying that they hang the jewels glittering like stars in the first magnitude. It is a wonderful sight to behold. Like if we now arbitrarily select one of these jewels for inspection and look closely at it, we will discover that in its polished surface there are reflected all the other jewels in the net, infinite in number. Not only that, but each of the jewels has its own unique properties. So this is the talk of, this is a place from which that Maya Jal is coming. The like, so you cannot really comprehend what is happening, because you are seeing one, but is that the whole or is that the part? Like, we are not able to make out. Because I do have an interest in stories, that is why I got into the story part. So let us look at these Lindenmayer systems. This Lindenmayer systems is one which we see it in, this is the very simplest of the way to look at fractals. This is one person named Lindenmayer. They have found out a model of the plant growth. This is a biologist who have come with and put all these Lindenmayer systems. This is all about plant growth. So we can describe how a plant grows. It's a parallel rewriting system. So you write one structure, then you keep repeating the same structure again and again. Like there are programs, these are done with the pictures which you see here, they are done with the Lindenmayer system plugins from this graphics program like Inkscape. This is done in Inkscape. Yeah. So they have this recursive nature. So it's like tree branch. You take one branch, that branch, one part of that branch gets replaced with an entire new branch. So this is where the self-similarity comes. These are fractal-like forms. I don't like being a purist. I don't know whether to call it. This is not coming from the complexity part of the fractal, but these are more of repeating the self-similar pattern. So fractal in itself is about self-similarity. So these trees are giving you a feel of how self-similar patterns come and how tree growth is modeled. So L systems, these are popularly known as L systems. So if you look at somewhere and then see Wikipedia also, you can look at Wikipedia L system. Maybe I'll open it right away. So there's a grammar that they use for, okay, so let's see. So you see these kind of trees that you can grow by using this grammar. So what they do is they are replacing. See these kind of patterns, you start from somewhere. So you have A, B, then you keep replacing and then keep adding. So you will keep building these patterns. So over the time, what you keep building, you will get trees and patterns that you want. And you can define how you want, whether you want to do a Fibonacci fractal or whether you just want some polynomial way of doing, you can do many of these things. This is the biology part of it, how plant growth is modeled. Very simple structures, and the method behind is also very simple. And now let us get into this complex numbers, how these the complexity and the complex numbers, this is coming from the complex number only, that complexity is coming, that small changes and large changes to the output, this whole concept is coming from complex numbers. I believe some of you, at least coming from some we have studied educational background, will be understanding what is complex number. So in that, what we are talking about, there is an imaginary part, what we call as like the I, that is square root of -1, which you cannot compute. That square root of -1 is where all this complexity and complex number comes. In that you will have one real part, and then we also have an imaginary part. And the imaginary part is the one which contains the square root of -1. So this is the basic representation of a complex number, like nothing new. Many of you know, but this is what really gets you into these fractals. What happens is a whole lot of magic comes into picture when you begin to iterate over these complex numbers. So when I wrote this Cn, it means the nth complex number. You take any number, say C0 or C1. So you square that number and you add a constant to it. The constant could be real or complex once again, and you get a new one. And then you keep repeating. It's like a for loop. You just put a for loop, and then you say, okay, if you say that this is the one complex number, that complex number equal to previous complex number squared, and then added one constant to it. That's what the iteration that we are talking about. The same iteration that we talk about in our program, the same for loop and while loop. So this is how we keep iterating. So now when you keep doing this iteration, you can start with a variable, that is your complex number C, you can put a 0, and then we are putting a constant to it. You square it, then you add a constant to it. That becomes your next number. Then you continue. So this equation of iteration, that will give you very beautiful patterns. That is a item which I am going to show you right now. So what we will see some examples of how they will get into if we plug in different values of C for this constant. So let us look at one outcome. This is nothing. You will not be surprised by seeing it, but then let's understand. It is the same principle. So you take the C0 square plus C. So we will start with 0 for your complex number part, and for the constant part, let us look 1. Like here, the imaginary part is 0. It is fully a real world part that we are talking. It's all real numbers. So what will happen is you do 1 plus 1, you square and add, then you will get a 2, you square and add, you will get a 5, you square and add, you will get next number, you square and add, and you keep going. So what will happen is it will explode too quick. The number grows too fast, and then they grow too fast and it will go out of your control. So you are not able to do anything. Because you are not able to compute, you are not able to hold that number. If you are doing say 10,000 iterations over this, or say 100,000 iterations over it, then you can't hold it. It is all somewhere. That's what you will see if you are looking at this is your starting condition. And now let us see one more starting condition. Say we start with a -1. You start the constant to be a -1. Then you say c square plus c, so you 0 plus -1 -1. See, -1 you keep square, and then you add square the previous value, and then add once again the same constant -1, then you got a 0. 0 -1 you got 1, and then that -1 square is 1 again, and then another -1 you got 0. Like you don't have to go too far. You see that the same thing is repeating. So it is just oscillating between two numbers here. It's just going between -1, 0, and then that's all what is happening here. So this is your outcome if you start with -1. I'm not telling any complicated mathematics. It is just basic. You square a number and add another constant to it. In fact, the whole world of these fractals and complex numbers, the equation is very simple like this. The beauty is coming when you keep iterating and keep doing it again and again. And then this is another pattern which you will find it very interesting. So here you start with a -0.5, a fractional value. Then what you will see is the number keeps oscillating between some constant, but the value is keeping on coming down and coming down. And here, this is where your iterations becomes more beautiful. Here what happens is the number keeps reducing, but it will never reach 0. But then it is keeping on reducing. So your dimensions will keep reducing, but then it's never reaches 0. And how this fractal or that Mandelbrot set came into is, if you keep iterating this over a period of time, and if you keep plotting it like how you see it, the patterns will keep repeating itself. Over a long period of iteration, they will repeat. But then it never reaches 0. It never disappears, but the pattern keep repeating itself. So this is what we will see here in the previous examples which I show. You will see two things we will see here: Julia set and Mandelbrot set. I know some of you who are so much fascinated by digital signal processing and all. I think you would have some familiarity with Julia sets. So this Julia set is what you are seeing here. For the Julia set is one where if you start with the C equal, if you allow it to be a constant K, and then if you keep this E0 to vary from your starting point, that is where you will get a Julia set. And the Mandelbrot set is also very similar. This is a Mandelbrot set picture where you keep your Z0 as 0. You start with the complex part as 0, and then you allow your constant C to keep varying. The one variable which you are iterating over, you are putting starting point as 0, and you keep the constant part into another complex number, and then you keep doing. That is where you will get Mandelbrot set. So what you are seeing here is the various Mandelbrot set pictures I have created over time. Okay, at some time when it was November, sometime is that Mandelbrot's birthday time. So at that time, out of fascination, I had created all these Mandelbrot ones. So this is based on your starting point, you will get varieties of these pictures. That's what you are seeing here. With me or confused? Hello. Total silence.
Yeah.
My audience is there, right?
Yeah.
Okay. So this is the
Yeah,
Mandelbrot set. So get this. Thank you. So get these two terms. One is this Julia set and the Mandelbrot set. They are very close by based on how we are starting and how we are doing it.
So
Now
there
let
are
us see.
some questions, many,
Yes.
like
Yeah,
how
very
did
good.
you create the ship pick?
Pardon?
How did you create the ship pick?
Where is ship? Did I
Ship.
show a ship? Which is ship? This one? Are you talking about a ship, or you are talking about my
Yeah,
desktop?
fifth one, the orange color should be fish.
This one. This is also a Mandelbrot set picture, in fact.
From,
I'll show you some. Yeah,
no, from second row middle.
this one.
Yeah.
That is also a Mandelbrot one. See, these are all varieties of Mandelbrot pictures only. The same
You use
equation iteration.
Python code?
No, this one I have done with a tool. There are you can write Python code. If you are interested into Python, you will see enough of open source code for Mandelbrot set. You can take it, you can play around, you can put in PyCharm, and then you can see that. I will have some programs written in Python here. But these pictures I have created using a tool, like the tool which you can feed in your starting point, and the tool will do the iteration. Like you can tell your equations into the tool and then do that. So very simple programs like for drawing Mandelbrots, you will see them in the Git or anywhere. You just search for a Mandelbrot set Python program, you will see enough of them. Like CoCalc is Sage Math. There was a program called Sage Math, if you know, which was a cloud-based mathematics program, which they have rebranded it to, and they call as CoCalc. That is also some place where I keep playing around. So you can write, the program will be hardly 5-6 lines, and then have some graphics plotting, like how I had put before, right? I put some turtle graphics. So get some graphics for plotting it. Then you can draw any of these for creating these pictures. But I have used a tool and then done it. Okay.
One more doubt. Actually, I want to create from an image. I want to convert into Mandelbrot set.
From the image,
so, for example,
convert. Yes, read it. Tell me again. Image to Mandelbrot.
Yeah. From a normal image, for example, there is a home. If I convert to Mandelbrot, I will get multiple homes, like the one you see in second row, middle one. Multiple I will get.
I got it. Okay. See, yeah, you can do that also. In fact, some of the pictures when I show you, you will get that. What you want to do is you want to take one picture and then you want to distribute that over a Mandelbrot pattern.
Yes.
You can do that. You can write some programs to do that, or even the program samples but you need to spend some time, okay, like, because you have to adjust that weight, how it will look like. Definitely you can do.
If it's easy, can you show a demo how you created that this one, that middle one, second row middle one, the tool, how you created, how to create?
Right now, I don't think I'm prepared to show that, but maybe we can. I'll show you the tools which I have used. Then you could explain.
Thank you.
Yeah, I'll show you the tools, because I think that will take a little more thinking time, right? I should have mentally been prepared to. I prepared those material and kept it ready. Where it is the program, only one program I kept it there. I didn't keep so many programs ready in hand for this session purpose. But just Google around Git also, you will see enough of them. So you want to create a Mandelbrot set with individual pieces containing all these.
So why it is all different shapes? Is it because it's varying, that complex part is varying?
One is complex part is varying, and this is also, there is something that is called as a fractal flames. These ones are created using a fractal flame. I'll show you later as we go along. A flame is a way where you can mix a lot of fractal equation, mix of transformations, and then you can render them all together. But we'll come to that. There's an algorithm for that, a fractal flame. That algorithm I'll show you. Hold your curiosity. You are asking too detailed too early.
Go on.
Yeah. So these are the picture which I am showing here. See, when I say higher order, what I mean is, see, previously we told that we will square it. What we told is we will square that number, c square plus c. See, instead of doing a square, what if I do a cube, or if I do a fourth power or fifth power? So if you keep doing that, you will get different higher order pictures. That's what will happen. So what you are seeing here is higher order Julia and higher order Mandelbrot, other orders. So if you do c cube instead of doing a c square, then you will get these kind of higher order pictures. So that is where all those flowers pictures you see there, many of them are higher order Mandelbrot or higher order Julia. So these are like an order of 3, order of 4, order of 5. That's what you are seeing. So like this, you can keep going with a higher order Julia or a higher order Mandelbrot. Okay, now let me listen to questions and anything else that we want. And programs. Okay, I'll show you some program later. Ranjini, any more questions are there, or should I look at the chat?
No, I don't see any other questions on chat.
Okay, let me give a pause. I'm waiting.
I think we can continue.
Continue, or should we take a small break and continue, or because we have planned for 2 hours, so should we have a small break and continue, or continue as it is? I'm asking a question. Anything is okay with me?
Yeah, I believe we can continue.
Okay, then let us continue. Some are asking what is a tool that you are using, and then there is share the slides, or is the meeting is getting recorded, so I believe Ranjini will share it.
Right, this will be posted in the Women Who Code YouTube channel. The recording will be available there.
Okay, then let us look at other balance part. So this was a logical pause which I had put there, if at all we want to do a break time. So let us do a fractal animation. This is just for a fun time that you can see. I use this program called Kaios. Okay. This is a program named Kaios. So there are a lot of programs which you search around, you will get many of them. So this is a Zoom program which will get you to understand what, like if you keep going inside again and again and again, then you are repeating, and the self similarity, how it is coming. So if I just click inside, see, you can see a lot of patterns are there. The whole picture looks the same. And if I go inside and then explore certain places somewhere, ultimately you are getting into same patterns again. See what you started with, you are coming there again. Or maybe you look at these eyes of the picture somewhere. This is a very rudimentary program, not very elaborate with respect to the graphics. This could hang and crash and all that is Kaios program, but still, since it is a free program, I am using it. See, you can see this. And there are very, the same pattern will continuously emerge. That's what we are seeing. So it will never end. You can keep going inside. Let me try some other random example. So I hope it will load. Writing programs, though it is interesting, there is only so much of limited in writing programs. Okay, this is too much of a 3D. I'll get something which is simpler. Okay, these pictures you see, colors. Okay, let's see this. This one also, if you go inside, this, yeah, these individual patterns, see this area, you will see it as the same structure as the whole thing. So you can keep going inside, and as you go inside, you take it one area, one structure inside, you will keep seeing the same structure again.
Oh, super.
That is what we call as a self-similar patterns. I have not written this program, okay, but writing this program is not too much of a challenge, like, because it is the same item getting iterated again and again. So you walk inside again and again, you keep getting the same pattern again. So this zoom is what make it ready. So if you came here, now you look at this pattern, you are again back at the same. So this is what that Indrajal picture that you were seeing. It looks like the same thing is reflected again and again on an infinite reflection onto that pearls that which they are talking about. So in effect, what you will see is you do not know how far you have gone into it. And even if you keep going infinitely inside, you will get into the same place and you do not know where you have reached. That is where that Mayajal and Indrajal is coming in. See, I'm retracting and then coming back into where we went into. Okay. So these people have given some sample programs. So you don't have to depend on the sample program. You can also pick some equations of your own. This one also gives this calculation filters. You can put your own equations here, this formula and all that, right? They have some standard ones, but you could also create your own user formula and then do what you want to do. You can put how you want to make it your own. But be careful, if you are not little bit careful, it could even get into infinity and then divide by 0 and all that you can get into. See, now I am retracting back from where we were. Ultimately, we will come back into same. We'll see some other example. This is just fun time to play around. This was again your same Mandelbrot. See, this is another picture. If you go inside again, you will see the same pattern repeating. That's the whole concept of the whole fractal itself. These are beautiful, very colorful ones, no? I just tried different colors. Green. Okay, dark green. I don't know what colors you like. Usually I like bright colors so that it is easy and interesting to see. This is what I was telling about the concept of infinity and self-similarity. So if you walk into one building or if you walk into that infinity, you keep walking. If you come back, again you are coming back, but there is not an end. So I thought I will show you some samples of.
It's kind of a maze.
Maze means, yeah, maze is like maze chuba is, maze means you can get lost. Like you have to go through some specific path. Yeah, this kind of a maze, maybe should be.
Means the location is not known. Means we are going somewhere.
Going, and it is infinity.
Yes.
Because it is the same thing that repeats after a while.
Yeah.
So how many steps you have walked, you do not know.
Yeah.
You don't
correct.
know where you are, basically.
You don't know where you are.
Yeah, that's why I thought it is kind of a maze, but it's a beautiful structure.
So this is coming, but you saw that equation, right? It is just take a complex number, square it and add a constant to it.
Yes,
that is all that is there.
Yeah.
It square a complex number and add one constant to it.
I didn't imagine that a small equation can do this much wonder.
Yeah, that's what I also got fascinated into all this. Like we have studied all our engineering mathematics and we have studied
So many
all
mathematics
DSP,
equations.
and the equation doesn't fit in our book page and it will still go. Whereas here it is, you don't have to write equations that don't fit into your book page. It will fit in a very short line, but then you get lots of beautiful infinite patterns out of it.
Yes, it's very nice.
You people, some of you who are part of my WhatsApp groups and all would have seen some pictures and patterns. These are coming from all these only. Okay, so let us stop this playing around with the Chaos program. If you are interested, you can take a look at install this program Chaos, then you can have a feel. They have enough of samples, or you can write your own. See, this is what I was telling when some of you were asking, do I write the program? Usually in my early days, when I was interested into all this, I used to write programs. But then over a time, the charm of more than writing program, it got into like playing around with that equation. So these days, what I do is I take this, then I try to adjust formulas based on what I want to do, and then visualize more, because that is faster. Only so much time I can spend. See, I also have my full-time day's work. So that is one reason that I write only small programs, not huge programs.
One doubt. So in case of image is array of numbers, pixel values. So
Yes.
each pixel value, should I convert into complex number or?
No. See, you get, there is I'll show you an algorithm later. See, whatever I showed there, the coloring, you get that X and Y, right? In a complex number, you have an A and B, right? That represent a point in a complex plane. If you take a complex plane, you can represent the real part and the imaginary part as a point in a complex plane, right? Okay, so you can take that point. That is the way it is. There is a coloring algorithm very specifically. In fact, these numbers, they are called prisoners and escapees. That is the way these numbers are called. The escapee numbers are the ones which will keep increasing. They become fat and fat, and they go off to infinity. Like previously I showed that squaring and adding, that equation part. So those numbers are the ones which we call as escapees. They escape to infinity too quick. And the prisoner numbers are the ones which we call as the number they stay confined. They never reach to zero, and they don't go and then go outside. At the same time, they are confined. They don't reach zero, and they don't escape to infinity. Those numbers are the ones which are known as prisoner numbers. Like I didn't want to get into that level of detail right now. That's why I stopped. Those are called escapees and prisoners. So based on the coloring algorithm, there are multiple coloring algorithms. The one simplest of coloring algorithms what you could use is you take a set of colors as your color palette, and then you can color it based on usually what is done is what is the tendency of that number to escape into infinity, or what is its pace of escape. So if it escapes fast, at that pace you start changing your colors from your coloring palette. So that is a coloring algorithm that you can use for coloring these pictures. You pick from a palette and then do it.
Oh, okay. Thank you. Is there any online tool can we see this escape and prisoner?
See, I think you will have to read. See, like what I showed, the complex number, right? If the number becomes, like if the real number, if the real part become, if you score, certain patterns of numbers will become escapees. So certain patterns will stay, they get confined. Like I showed you before, right? In our previous equation, some examples, some numbers, when you keep squaring and adding, they keep growing. Some of them oscillate between 0 and -1, whereas some of them you emerge into a pattern. They have a tendency to come closer to 0, but they never reach 0. Just before I showed those squared numbers, squaring and adding.
Yes.
I think I showed those numbers, right? These ones. This will stay. These are on the periphery. These ones are the ones which are going too far. So they escape. And this one, they stay confined, but they don't reach 0. That is where they call us prisoners.
Get this effect, which numbers we should select?
No, you can start from any complex number. You can start from anywhere. In fact, if you start from a complex number, you will actually reach there. I was showing those real numbers for an example to understand what are the properties of that complex number that can happen. And if you start at a different starting point, will give you different patterns. That's what the whole concept of chaos. Small change in input condition can give you large change in the outcome. The concept of chaos itself is there. So if you ask from where should I start, you start from anywhere. Based on from where you start, you will get different effects. Did I answer you?
Yes, thank you.
But spend some time reading. I think it may be a little more deeply involved. This session is meant only as an introduction to introduce the concept of all these. Okay, the tools, I use some more of tools than what is listed here. I use some other program called Mandelbrot, and which are like these Mandelbrot sets. There are very specific tools. They are very slow in executing. That is why I didn't put it here, because unless your laptop is quite fast in executing, then you may find a problem. It will be very slow. But these are some of the tools that I use. This Chioscope is talking about that attractors, which I was talking about. Then Chios is a zoom-in program that I showed. Apophysis is a fractal flame rendering program. And there are also paid programs like Ultra Fractal. So you could search around for any kind of fractal rendering program. You will see many of them. You could choose what you find fascination. Like I got stuck with apophysics. That is something which I somehow generally found it interesting. But then it is personal taste. I'll show some pictures which I have created. So maybe we'll see some of them. I put some pictures here. See, this is one image which I have created. I thought, okay, why not I show off some images which I have created along with this session. So these are one picture which I had created. This is another. This all has the same pattern. If you see, the cell similarity is seen. And then this is another one which is created. Like if you look at this one branch, the one branch again has the same structure. If you see carefully, that's what you will see. Time pass creation. And this one, I still like the color combination of this, that blue and purple. And this is something which, okay, a bouquet of flowers. And these are from samples from the apophysis. These are rendered here. And this is another flower. I like this flower somehow. This, because I get that feel of that stem and the flower.
It's like a bellflower.
Yeah, so whatever it be. So this is some other flower which I keep creating. And then there is a tool. Maybe I should show you the tool which I'm talking about. Like what I did was I opened and I kept some program which are ready. Okay, so this is a program which is called Apophysis, which I keep using. So if you select what kind of a the density you want for showing here, you can select 500, because the more you go, the picture becomes more and more clear. But then it will be slow. So just for getting a preview, you put something small for your rendering. Otherwise, the rendering takes time because it's an iteration, right? You keep doing it. This I just wanted to show some example. Okay, so what you could do is in this fractal flame rendering, this is a flame rendering program. So this F that it is showing, that is the editor of the flame. So you can come here. These triangles are just representation. The triangle doesn't mean anything as such. Okay, so these are all various variations that you can use. You pick some variation, red one, and you can put various weights to it. Over time, you will get a feel of what these variations will give. These are Julia, bubble, polar, all that. I'll tell you all this. These are all variations that you can put onto these individual flames. These are called flame triangles. You can add multiples of flame and then add some properties to it. Then take this another. So multiples of them you can create. It's not, it will take some patience. Okay, don't think that the moment you start off with that you will get beautiful flowers and all that. You will get some random, like you don't understand anything. You will just get some bundle of pixels which will not make any head or tail out of it. You just get, because it's all to do with chaos. So over a period of time, but the chaos has hidden patterns of these beautiful flowers and gardens and all that. It will take some patience. If you are interested, then spend time, you keep playing around with it. At some point you will get it. It's not that okay, let me start a flower, I sit down and I get into somewhere. Okay, you enjoy the process. At some point you will feel happy about something, then you stop it. That's what I usually do. Like usually I don't have a target of this is what I want to make or something. Like I keep playing around. When I find something attractive, I keep it there. Otherwise, okay, leave it and continue, discard it. And occasionally I also play around with random. See, you can create a random batch. You make some random, you may find something from the randomness also. In fact, this whole thing is all about randomness. So randomness is something which you will like it. And then you could come to these tools and the settings. You could import some variations from wherever you want. Linear is a basic that you may want. And Julian is all that, the Julia set which I was talking about. These are all variations of that. So pick these kind of things. You can select some, pick some random, do whatever you want. Some butterfly transformation you can do. But it takes some time and patience, and like it's not about like how in the same way of looking at the chaos theory that we were talking about, like you can't predict the outcome. That is a whole understanding of the complexity and chaos theory. Based on where you start, if your change is very small, your outcome could be totally different. So if you think that you have, this is the outcome I want, and then you want to reverse work, that may be more challenging than you start from where and then you go along with it and reach to some outcome. Because the whole concept of complexity and chaos theory in itself is that, like sometimes people say, right, don't look for your results and don't do your work. It is the same way. You keep doing, at some point you will get it beautiful there, and over time you will get experience and you will know what to do. But then it is never that, okay, like you keep a target in mind and then you keep working towards it. Like that's not the ideal way to work on this. Anything else? Any questions?
One group of patterns can be removed from the result.
You can, but the thing is they are all interfering with each other. Like how I was telling, right? Like the moment you remove one, you may not get what you have in mind. You may get something totally different. You can remove. See, like say you take this, you come here. These are random. Okay, I just picked random. Say you take this, you remove them. you get something else. But then you may not be able to, these are all linear. So you may get very similar to similar. But then the moment you remove something, it's not like one thing you remove, because they all interact with each other. That is what the whole concept of system and complexity itself. They interact with each other to give you a result which you did not think of. Even this complexity iteration is also the same. Like when you remove one small effect, the same butterfly effect. Like if the butterfly had not flapped its wings, the hurricane wouldn't have occurred. Like if you talk about a butterfly at a hurricane, you won't be able to see that relation so quickly.
Yeah.
Like they are too far relations, right? Butterfly and hurricane.
Yes, yes.
But now if you think in a complexity terms, then you can comprehend, okay, that small butterfly flapping the wings would have created some air vibrations that would have got propagated. Maybe that air vibration with other effects got amplified, and then it would have caused your hurricane. So it's not that one item that caused all your effects.
Yeah,
that's what sometimes even in our life is also many times it's like that. One small thing which we did, if we had not done it, probably that large output wouldn't have happened. It takes you along. That's a way to easier to look at it.
Okay, got it.
And now I think I want to show you that the story behind that is the flame algorithm paper. So there is a paper. This is what this flame, like how I, yeah.
And that is a question I posted. Could you please open that link and see? Yes. Actually, I want how to know how to map the picture's color into fractal color, fractal image color.
See, there is a coloring algorithm. That's what I showed you before. How to map?
No.
Mona Lisa picture color into fractal image. Okay, let's read. I'm not understanding what you're asking, but let us see.
There is a picture of Mona Lisa. I want this one. That is the above image. She's wearing a brown gown. The same color how it is coming here back. You told they are taking X and Y coordinate.
So this one, see what you are seeing here, this may not be Mandelbrot, but this could be a variation of Julia, what I showed you, okay. So this one is what they are doing is instead of looking at it as a point, like I had a picture there somewhere, the whole eyes, one of an animal's body full of eyes. I had a picture somewhere there around. See what they are doing is, it is a mix of graphics. See, usually, like I'm a purist. See, that is one reason which I did not get into this. There are a lot of people who do. This could also be with, you take one picture and you use that as a point and then doing it. I am more of a purist person. So all the time what I am doing is just raw fractals. There are a lot of people who take fractal images and they blend it with other Photoshop GIMP kind of things. But here from the picture, what it looks like is they have taken a fractal iteration and then instead of drawing that one point there, they put the whole Mona Lisa there and must have scaled out. That's what it looks like. Okay, now I got what you were trying to ask in the very beginning. I'll have a look at this program. Anyway, interesting. Yeah, but I think I'm too much of a purist person, so maybe I didn't get into this. In fact, I was staying away from looking at mixing Photoshop and GIMP with these pure equations. All the time, like, so I was staying with the pure equations. I think you can leave your contact somewhere in the window or somewhere. Or you could pick my name from somewhere there, and then we'll have a look later after these sessions.
Sure, thank you.
And give me 1 minute, let me keep a note of into my system for your reference link. That's my OneNote. I'm just taking a time for putting my reference now. Yeah, but probably it is time that I've also changed a little bit out of my purist mode. Like somehow I feel that I should not be doing that. mixing two things like this, no, picture as well as this. I have seen variety of people who do what they do is they take a some kind of this is one way. Do the other way, like take a picture and put a fractal pattern onto the picture. This one has taken a picture and put the picture onto the fractal. Let me come back to our place. Okay, this is the algorithm which I was talking about. The fractal flame algorithm. This one I'm only introducing you to it. I'm not explaining the algorithm, but I would suggest that you read it at some time for your leisure. See, this Quadrevs, this is a one who is, he also runs a website called Electric Sheep. So you could look at that website of Electric Sheep, but then the base is coming from this flame algorithm. Like apophysis and ultrafractal and all that are flame algorithms. So what they do is they call these variations or transformations and then mix all these variations or transformation into a single one. Like I don't get into equations, but I would just tell you the concept. So he explains lots of transforms here. Each of these transform, what does it give you? You can put coloring. The coloring algorithm is explained here. Color or the density, you can put each of those transform can have different amount of weight attached to it. So here they explain some of these transforms which can be used. Motion blur, these are all property that you can attempt to do it. But this paper is something which I would suggest you read it if you have a lot of interest on how to do this. Where the paper had those pictures? Okay, catalog, variation catalogs. Okay, this is a linear variation. But then in apophysis or ultrafractal, you will get lots of variations. Like you will see it in the open source world. Many of them you could pick up. These are different variations. Then you can pick a mix and match of variations, apply the weight, and then apply them differently so that you can create a whole variety of patterns. In fact, the apophysis program that is doing this work only. This is a flame rendering program. Pick all these flames and then do it. So they are explaining some basic flames. What do you get it? I think I was showing that apophysis program, right? Let me open some examples. I just picked some flowers here. Okay. These are Julia actually. The way you are distributing and seeing it's Julia. But it is a very heavy one to render. And one more reason why I say have patience is this is usually slow in rendering. So if you come here, then if you click on them, they will show you what is that. This is Julia is there. That's what you see here. It's Econ and Julia, similar to the green one. The individual transforms which they are talking about in that fractal flame rendering program. So if you get to this flame rendering algorithm, then you will get what the apophysis or ultrafractal is doing behind. These are some samples of variations which they have given. They are all different equation. How do you transform one x and y into another x and y? By applying various transforms here. Some are with constant, some are with like some trigonometry equations are applied. Based on creativity, people are creating lots of patterns like this. Okay, there's nothing like you should look at one or anything. So this Scotrave's paper, which is called Fractal Flames, that's what explains these kind of variations and who has come out with that algorithm. Electric Sheep is the website. What they do is they are actually borrowing computing power. You can download and install that Electric Sheep, then they'll do some work in the background. Let's come back. Any quick question or shall we go further? Hello. Silence. Okay.
I think we can proceed. Yeah.
You can proceed. Then why do you want to do all this? That is your next question. One, for example, number fancy and hobby interest people like me. That is one. And in general, there is this aesthetics that is associated with this. And design, these fractals are also used by a lot of movie makers. If you see these Barbie movies or Disney movies and all that, there are people who use that for creating artificial forest and artificial flowers and those kind of things. The movie makers do this for fractals, for creating those sceneries, artificial sceneries. That is one way people use. Designs means, if you see, if you look at in YouTube, you will see some designs which are inspired by fractals. And then antenna design by people use this is I think that is Nisha's favorite topic. Nisha was in the meeting. Antenna has this, people want to have a lot of surface area, and that is when you will be having this signal capturing capacity. So for that, some people use this fractal pattern so that your surface area becomes more. And data structures, you can use this. And maybe there is medicinal usage on how people may want to follow the path of various things in the medicine, like maybe knowing that biology and the human, a lot of the human structure is fractal patterns. And architecture, there are also some people who design this architecture, I mean this building architecture kind of things based on, inspired by fractal patterns. There was a very beautiful video of this architecture inspired by fractal patterns. And then Zoom, this is one friend of mine who is made this Zoom. So I had told him that, okay, I will play this video during my session. Okay. So I will show this one, YouTube video. Is the audio also shared, or is there something I should do for that? Hello? Ranjini or someone, can you please confirm whether the audio from the picture is
Audio
also
is there.
there? Okay, then let me play. Just enjoy watching. It's just for a relaxing time, okay? It's just become loading my network problem. I'm facing this network not so great. Hopefully it will come.
വരുന്ന പോലെ
Did I?
Wait. നോക്കിയാൽ മതിയായിരുന്നു. എന്തായിരുന്നു പറഞ്ഞ കുട്ടപ്പോ കോഡ് വരുമെന്നോ?
ഒരു കോഡ് വരും വന്നുണ്ട്.
ഇതിനകത്താണോ?
അമ്മയ്ക്ക് വരണ്ടേ?
My full
It is playing very slowly. I think maybe network problem.
done. Nice video, right? People are there.
Yes.
Yeah, so this is one person whom I know. He creates this. I have not grown up to this level of creating things. One is because I still haven't started to pay money and buy programs for doing all this, because if you want to do this level of Zoom and Fractal Zooms, you can look at in the YouTube Fractal Zoom. You will get a lot of videos. But this is something which, because I know this person, I put it. And I haven't grown up to that level. Maybe I should try with this much of interest, spend some money and buy some ultrafractal. Ultrafractal has these kind of features where you can mix music as well as create this Zoom inside. The open source programs won't take you to this level of detail.
It's a very
But I like
interesting
this
field,
picture.
I guess.
Yeah, I think if it has to hold my interest for this much time, then it is very interesting. And I'll also show you something. Yeah, in fact, I am coming to more or less towards the end. I'll show you something which is even more interesting. That is, where do I have? See, if you look at Google Earth, okay. I was telling that a lot of patterns inside in nature, they are all fractal patterns. I was telling that right before. So these are captures from Google Earth. If you are looking at Google Earth, you can see, then you should be able to see fractals, right? So these are all patterns. So I only have put some patterns from this country, India, where I don't know where exactly these are. They must have given the coordinates somewhere. So I liked that sentence that they have written there also, the Google Earth captures. These are like you play around on Google Earth, you go find out pictures in Google Earth, and then you will see them. These are just screen captures from Google Earth, okay. So I found them very interesting this is public domain only. So I thought, okay, maybe I should show it. See what he is writing there is fractal geometry that will make you see everything differently. There is a danger in reading further. you risk the loss of your childhood vision of clouds, forest, flowers, galaxies, leaves, feathers, rocks, mountains, bricks, whatever it be. But never again you will see your interpretation of things as quite the same. But I don't know with me what has happened, whether I lost the child or after I grew up in the last, from 2016, I think I'm doing it for past 4 or 5 years. So whether I regained my childhood or whether maybe for small children who may lose their childhood, maybe you will regain it again. But these are Google Earth capture pictures from various locations. These are from various locations in India itself. Like you can see how these rocks and rock formation, or this must be some rivers or dried up patterns, how they are becoming fractal patterns.
Amazing patterns.
This is what we call as the complexity and the emergence philosophy that being talked about itself. Like it gives you a different outcome based on where you are starting, and small change is enough to create huge variation when it is applied over a long period of time and in that to a larger system. Like these are Google Earth captures, which you may not even think of what is there. See, they pick this one area and how it has come. Very interesting patterns. So these are all what I'm doing for time pass interest for time. Then I have put some references here, maybe Fractal Foundation. These people have some tutorials and all that if you want to understand basics. See, Fractal Foundation is a very interesting place. You can, they have a lot of resources there. Like they even have some tutorial, explore online fractal course. Okay. Like some of the pictures I showed you are taken from this online fractal course. They explain what is chaos, strange attractors, but chaos and strange attractors and all, I have learned from some or the other maths book and maths packages, but then you could pick from anywhere. See, they like Fibonacci sequence, you must be knowing this Fibonacci sequence. And this rabbit breeding story, you must be knowing it. You could go and pick and then see where they are. They're very interesting resources, golden ratio Fibonacci series. You will be knowing all this. I don't think I'll need to explain all this. But then these are interesting materials. So now I'm waiting for questions or comments or feedback or opinions or fascinations or whatever it be. And if you are interested in seeing some more of my pictures, I will show you some more of my pictures also.
Yes, I would like to see the pictures.
You want to see more pictures? Okay. I have no problem in showing off. So let it be. So these are things which I had created in the recent times, maybe sometime. What you see in the desktop, you see that desktop picture, right? Right
Yes.
now. That's also one such picture only.
Wow. Somewhere in the galaxy looks like.
Yeah, some people say that it looks like some chandelier, fancy chandelier.
Yeah.
These are some other pictures. Where do I say play next?
I'm planning to start a graphic business t-shirt.
You want to do a graphics design, no?
Yeah.
These are something which I have created recently in the Christmas holiday time. This picture, I like this one very much. It's extremely simple, but it looks very nice. Somehow I like the color combination.
Many, and there is one request to put all the references in the chat window. If
you want to copy and put the references in the chat window, okay, why not?
And the slides, will it be shared?
I don't know whether I should. Let me think of Shiba.
Okay.
The chat. Okay, references I have pasted here itself. Okay. We were seeing pictures, right? Yeah. This one also, this is something which I like so much for the reason that even that edges that you see there, all these are from fractal rendering. It is not edited in Photoshop or somewhere.
Oh.
This one I have created so many with different colors. because that was a time when I was getting interested into colors. You can see that fractal geometry. Once I have explained, you will see that. See the bigger pattern, even the smaller patterns are the same. Whatever you see around, right?
Yes, yes. So nice.
Beautiful they are.
The mathematics itself, it is influencing.
This, I think I got into it from my number fancy, in fact. See, these are pictures which, this also, I like this. So many flowers, right? That is distributed over Julia. Not all of them are great pictures. I'm just showing my folder. Like some are very interesting, great pictures. Some I wouldn't have spent much time, but created. All these bokeh pictures also I like. There are so many here, Shubha.
Okay,
In
okay.
fact, my system is having full of these kind of pictures.
It's so nice. It's good.
I think maybe I'll show something which is this one, something which I'm very proud of. This is something which, because it was a challenge to differentiate that flowers blue and the plant green and keep it there, right? So somehow this one is something which I like it so much. But maybe for the viewer, it doesn't make so much difference. But then
Yeah, maybe the programming or the challenge is differentiating.
So I don't write programs for all this. I pick and choose programs and try to play around to get what I want.
Yeah.
And I'll also show you some flowers. That would be some single flowers I had created. Not that one is better or another is better, but see this one. This is something which has like caught my fascination, like especially the edges and the glow and all that.
Can you do and show once like how you do, what all you select? How much time it will take to
See,
create
you play
something like
around. I showed this Apophysis program, right? This one.
all these from Apophysics
All
only?
these, whatever I showed, are created by Apophysis. They're hidden there. It's not that you don't get into a flower or something immediately. Okay, they're hidden there. You may see that random. You lose your patience. It's just colors. Like when you can lose your patience also.
She has
when
spent
I-
around 4 years, I think. So
That's
she
from
well was-
2016. I've been doing this. Okay.
for 5 years. Yeah, around 5 years she has spent.
But then it was a side work sometime or the other. So these are all whatever captures have come out of all this.
Yeah, I'm sure within a day we cannot do anything.
No, but you enjoy the process.
Yes, yes.
But not depend so much on the outcome. Like when you look at, I want to create some output, then only you will get frustrated. Okay.
Yes, yes.
Okay, what else?
When I started to draw, hold that blue color picture only.
Yes.
And that one, when I started to draw, I got something like this, not on the center one, at the edges. I could see some spots alone. Was it because of the picture or it is?
No.
I have
See,
not
that is what,
detected.
see, you get back to the basic. First, you put that concept into your mind. It is chaos. It's complexity theory and chaos. So beauty is there, but then it could be there hidden somewhere. See, it's like small changes can give huge change in the output. Small change in input can have huge change in the output. So if you just start from somewhere, you may not reach anywhere. Okay, that also could happen. Get that concept of chaos theory deep into you.
So
Like you may
when I
just see random.
didn't get anything, I have to change my constant.
You play around with that constant, the parameters, and even that location of that triangles. Which program are you using? Apophysis?
No, I wrote my own Python program.
You wrote your own program. I suggest if you like, I don't know whether that is a way everybody wants to do. Like when I started, I used to write my own program, but then I only used to do simple thing like Mandelbrot set, basic Mandelbrot set, or do that Siren-Pisky triangles, or I only were doing very small simple program with my own program. But when it reached complex one like this, I started to use these software packages. because it can be too much overwhelming, both to focus on the program as well as on the parameter. So the complex ones, this kind of difficult ones, I don't get into with programs of my own. In fact, these days I'm not writing programs. I think other than trying to understand, when I want to understand that Mandelbrot or what is the mathematics behind, then I may write some program. But to get some pictures, I depend on these tools. Yeah, but it all depends on how much patience you have.
Okay. Leave your contact or LinkedIn handle or something so that we can get back.
Yeah.
Slides also, you can delete any confidential information and share it.
I don't know what is confidential, because these are all personal interest. There may be, the only thing which I have a fear is there may be things which I would have copy pasted from somewhere from Google and I would have played around. So they may have some copyright, which I may not be aware of. See,
Maybe we'll use it internally. You can share, we'll use it internally, but you can refer it.
I will give my LinkedIn handle. Okay. So that is me.
Fractal group you mentioned.
Fractal group, I am not the admin of that group. Okay. Let me check that group. I'm not the admin. The person whom I showed that video, right? That person is the admin. I'll look up that group and give you.
Thank you, and I learned a lot. I'm into fractals last 1 year. For hobby I started, but I didn't go anywhere. I just saw some
See, in
few
fact,
spots.
I didn't have any intention to do any of this. Okay. It's not that I started liking fractals or then I did something. No, I didn't do at all. I had a fascination for numbers. So from numbers, somehow I got into it. That's what happened. It was never with the intention of doing fractals. See, I pasted a group that is for the group. The LinkedIn group is there. I'm not maintaining this group, but I just follow that because the video which I showed is from that person who maintains that group. But I don't know what is happening around. Maybe if there are enough number of people, maybe we can start a separate group, because these are some or the other people outside. Like we could start a separate independent group and then keep it. All my groups which I maintain are cybersecurity groups, not all these. Okay, what else? Ranjini, should I hand over to you? I don't have anything for more from my side.
Yeah, if there are no more questions, then we can wrap. Are there any other questions?
One thing, is this recording available somewhere?
Yeah, it will be available in the YouTube Women Who Code YouTube channel.
Great, thank you.
Sure, thanks a lot, Minnie, for this useful information that we would not even have got exposure to. That was
in fact, that's also one thing. I don't see enough of people. Like I rarely come across people who have an interest into this.
Right. Yeah. But thanks a lot for your time, and thank you all. Thanks all participants who have been actively looking forward to learn more. And please stay tuned for upcoming Women Who Code sessions. Thanks a lot, all. Thank you for your time. Bye.
Okay,
Thank you all of you for coming in, because I was doing all this for my own interest. Okay, but then I'm happy to have an audience who is getting interested into this topic.
Thank you so much. Thank you so much.
Thank you. It was a great session.
Thank you so much.
Thank you.